This is a map of India, a foundational document of the modern age, charting a subcontinent of immense complexity. And this is the instrument we are told was used to create it. The Great Theodolite, a machine of brass and steel weighing nearly half a ton. An instrument of almost perfect precision, designed to measure the heavens from the controlled stability of a European observatory. Yet, the official history of the 19th century asks us to believe a different story. It tells us that this colossal, delicate instrument was not kept in an observatory. It was dragged, by hand, for thousands of miles, through impenetrable jungles, across scorched deserts, and hoisted to the peaks of the highest mountains on Earth. We are told this was achieved by men of grit and determination, armed with little more than ropes, elephants, and bullock carts. This is the story of the Great Trigonometrical Survey of India, a story of human endurance. But is that all it is? When we look closer, the story begins to unravel. The logistics become impossible. The timelines become fantasy. The narrative, held up as a triumph of the colonial age, collapses under the simple weight of its own claims. The map exists. The instrument exists. The problem is that one could not have created the other in the way we have been told. In this investigation, we will not speculate on who truly created this map. We will demonstrate that the official account is a fabrication. We will show you the evidence that proves the story of the Great Survey isn't just improbable, it is impossible. Before we analyze the journey, we must first understand the object at the center of this story. The Great Theodolite was not one instrument, but a series of them, commissioned specifically for the Survey of India. The largest of these, designed by the famed instrument maker William Troughton, was a monster of 19th-century engineering. Its horizontal circle was 3 feet in diameter, made of solid brass, and graduated with markings of such fineness they could only be read with multiple high-powered micrometers. The telescope attached was powerful enough for astronomical observations. The entire assembly, with its supporting structures, weighed over 1,000 pounds. 500 kilograms. We must pause here and consider what this means. This is not a field instrument. Field instruments, then as now, are designed for portability. They are made to be carried, to be set up and broken down quickly. They are engineered to withstand the rigors of the outdoors. The Great Theodolite is the antithesis of this design philosophy. It is an observatory instrument. Its immense weight and solid construction were designed for one purpose: stability. To achieve the microscopic precision required for geodetic survey, the instrument must be perfectly level and motionless. In an observatory, this is achieved by mounting it on a deep stone column, isolated from the vibrations of the building itself. But the Great Survey was not conducted from a single observatory. It was a chain of thousands of measurements, taken from thousands of points, across an entire continent. Each point of measurement required the same level of perfect stability. The visual evidence we have is sparse, but what it shows is deeply strange. We see engravings and early photographs of this colossal machine, perched precariously on wooden platforms or on the top of purpose-built masonry towers in the middle of nowhere. It looks alien. It doesn't belong. There is an immediate, visceral disconnect between the object and its environment. Look at the men standing beside it. They are dwarfed by its scale. Consider the complexity. The dozens of delicate screws for adjustment, the vulnerable micrometer microscopes, the finely balanced telescope axis. This is not a tool for the rough and tumble world. It is a laboratory device. How is it protected from the torrential monsoons? From the fine dust of the desert that would grind its delicate mechanisms to a halt? From the extreme temperature swings that would cause the metal to expand and contract, throwing off its perfect calibration? The official accounts offer no meaningful answers. They do not show us the specialized, shock-proof, climate-controlled container that would be necessary to transport such a device. No such object appears in any record or illustration. We are simply shown the instrument, miraculously assembled and operational in a place it has no business being. The anomaly is not just its size, it is its very existence in the field. Every principle of engineering and common sense tells us that you do not take your most sensitive, valuable, and heaviest piece of equipment into the most hostile environment on the planet. You design a different tool for the job. But we are told they did not. They chose the most difficult possible path. They chose to use an instrument that seems almost designed to fail in the conditions it was subjected to. Why? The visual evidence does not provide an answer. It only deepens the question. It presents us with a contradiction. a perfect instrument in an imperfect world. And it asks us to accept that this contradiction was overcome, time and time again, for nearly 70 years. The images themselves are the first clue that the story we are being told is not the whole truth. The visual anomaly of the instrument is unsettling. But it is when we consider the practical logistics of its journey that the official narrative dissolves from improbable into impossible. The centerpiece of the project was the Great Arc, a line of triangulation stretching over 2,400 kilometers, from the southern tip of India to the foothills of the Himalayas. This was the spine from which the rest of the map would grow. Let us trace this path not as a line on a map, but as a physical journey. The path begins in the dense, malarial jungles of the south. There are no roads. There are no railways. There are only narrow animal trails, swamps, and rivers. We are asked to believe that a team of hundreds of men carved a path through this environment, carrying a half-ton, fragile instrument. How? The official transport method cited is the bullock cart, the elephant, and the human porter. Let's examine this. A bullock cart is a rudimentary vehicle, with solid wooden wheels and no suspension. The violent jolting of such a cart on an uneven, hand-cleared path would destroy a delicate scientific instrument within minutes. An elephant, while powerful, is not a stable transport platform. Securing a half-ton, top-heavy object to its back for a journey through dense, uneven jungle is a logistical nightmare. The risk of the animal stumbling, or being spooked, is immense. One fall would mean the end of the project. This leaves human porters. How many men does it take to carry 500 kilograms? At least a dozen, probably more, working in perfect concert. They would need a custom-built litter, a complex cradle to hold the instrument. Now, imagine these dozen men carrying this immense weight up a slippery, muddy hill, or wading through a chest-deep swamp. It is not feasible. And this was not a single journey. This process of transport had to be repeated thousands of times, between each survey station. Now, let us consider what happened at each station. To get a clear line of sight to the next station, often 10 or 15 kilometers away, the surveyors had to raise the theodolite above the trees and terrain. This meant building observation towers. These were not simple wooden scaffolds. The records describe masonry structures, sometimes 50 feet high, built with brick and stone. Where did these materials come from, in the middle of a remote jungle or desert? How were they transported? How long did it take to build a 50-foot tower, just for a single set of measurements, before abandoning it and moving on? The construction of the tower is an immense logistical feat in itself, completely glossed over in the heroic narrative. Once the tower was built, the half-ton instrument had to be hoisted to the top. How was this done? With simple block and tackle? The immense, concentrated weight would put incredible strain on any temporary wooden structure. The risk of it crashing down was enormous. Let's assume they managed this feat. The instrument is now on the tower. It must be painstakingly assembled and calibrated. This is a process that, even in a laboratory, takes hours of meticulous work by a trained expert. Here, it must be done in the open air, exposed to wind, rain, and sun. Then, they must wait. Wait for the perfect atmospheric conditions. Weeks, sometimes months, would pass, waiting for a break in the monsoon rains, or for the heat haze of the desert to clear. During this time, a massive entourage of hundreds of people, surveyors, soldiers, porters, laborers, had to be fed, housed, and protected from disease and wildlife. They were a moving city, dependent on supply lines that, according to the records, did not exist. After weeks or months, the measurement is finally taken. The process then reverses. The half-ton instrument is disassembled, lowered from the tower, and packed for the next impossible journey. When you walk through the steps, one by one, the official story becomes a sequence of miracles. The cumulative improbability is staggering. It is not a story of human endurance. It is a story that defies the laws of physics, engineering, and logistics. If a project of this magnitude were undertaken today, it would generate millions of documents. Engineering plans, risk assessments, supply chain manifests, transport schedules, maintenance logs. It would be a mountain of data. When we look for the equivalent records for the Great Trigonometrical Survey, we find a void. What we have are the personal journals of the surveyors, like William Lambton and George Everest. These documents are compelling, filled with tales of hardship, encounters with tigers, bouts of malaria, and a relentless drive to complete the mission. They are heroic narratives, But they are not technical manuals. They speak at length about the scientific readings they took, the mathematical formulas they used. They speak of their dedication. What they do not speak of, in any practical detail, is how they moved the machine. The logistical solutions to the problems we have outlined are conspicuously absent. There are no detailed diagrams of a transport cradle for the theodolite. There are no engineering specifications for the cranes used to hoist it onto towers. There are no supply manifests detailing the thousands of tons of food and equipment needed for the entourage. The records describe what they accomplished, but they failed to describe how they accomplished it. The story is presented as a given. The movement of the instrument is treated as a trivial detail, when in fact it is the single greatest challenge of the entire project. This is a massive red flag. When the most difficult part of an operation is omitted from the records, it suggests the records are not a faithful account of what truly happened. Instead of logistical data, we are given a repeating narrative template. The story of the Great Survey conforms perfectly to the 19th-century colonial archetype, the triumph of Western science and willpower over the chaotic, primitive forces of nature. It is a story designed to legitimize colonial rule, to showcase its technological and moral superiority. But a story is not a substitute for a logistical plan. The vagueness extends to the finances and manpower. We know the project was immensely expensive and suffered from extremely high mortality rates among its staff, both European and Indian. Yet, it continued, uninterrupted, for 7 decades. Dynasties rose and fell, wars were fought, but the survey continued its slow, inexorable march across the continent. How was such institutional consistency maintained? How was knowledge transferred when the experts were constantly dying of disease? The official explanation is simply that they persevered. This is not an explanation. It is an evasion. It asks us to stop asking questions and simply admire the result. It treats the surveyors as superhuman figures who transcended the physical limitations of their era. But they were not superhuman. They were men, subject to the same laws of physics and biology as anyone else. An organization cannot function with such a high rate of attrition without a robust, well-documented system of training and knowledge transfer, a system for which little evidence exists. The official story fails because it is not a technical history, it is a myth. A foundation story. And like many myths, it glosses over the inconvenient details in favor of a simpler, more inspiring tale. The problem is that the details it glosses over are the very details that would make the story believable. The impossible story of the Survey of India does not exist in a vacuum. If it were a single, isolated anomaly, it might be dismissed as a unique, albeit miraculous, achievement. But it is not. When we zoom out and look at the great geodetic projects of the 19th century across the globe, we find the same pattern repeating. The same impossible logistics, the same glossed over details, the same heroic narratives. Consider the Struve geodetic arc, a vast chain of survey triangulations stretching for over 2,800 kilometers, from the Black Sea to the Arctic Ocean. The project, run by the Russian Empire, crossed 10 countries. It faced immense challenges: vast forests, freezing Arctic conditions, and inconsistent political territories. The instruments used were, again, large, cumbersome, and delicate. The official story is, again, one of heroic astronomers battling the elements to achieve a miracle of precision. But like the Indian survey, the practical details of transport and logistics through such varied and difficult terrain are sparse. The narrative focuses on the scientific genius, not the engineering solutions. Let us look at the United States. The U.S. Coast Survey, which later became the National Geodetic Survey, undertook the monumental task of mapping a continent. They faced deserts, mountain ranges, and vast, unpopulated territories. We see the same types of instruments appearing in photographs, perched on wooden towers on remote mountaintops in the American West. The story is one of rugged pioneers and brilliant scientists. But how did they transport tons of equipment up a 10,000-foot peak in the Rockies in the 1870s? The story is told as if the simple will to do so was enough. This pattern is not an accident. It points to a standardized method of operation, and a standardized method of storytelling. The operational template seems to involve using impossibly large, observatory-grade instruments in the most difficult field conditions possible. The narrative template involves framing the entire endeavor as a triumph of national character and scientific prowess, while meticulously omitting the enabling logistics. A key repeating motif in these global surveys is the construction of elaborate temporary structures. All across India, Scandinavia, and America, we find the remains of these survey stations. Often, they were not just simple towers. They were substantial stone and brick structures built to last. Why build with such permanence for a measurement that would take, at most, a few months? Why expend such enormous effort and resources on infrastructure that was supposedly disposable? The logic is inverted. It is as if the permanent, difficult-to-build structure was a prerequisite, a non-negotiable part of the process, even when it made no practical sense. The survey of Egypt, the measurement of meridian arcs in South America, the story repeats. European or American surveyors arrive with impossibly advanced instruments, perform miraculous feats of logistics that are never fully explained, and produce maps of unprecedented accuracy. The pattern suggests that the Great Trigonometrical Survey of India was not an exception, but a rule. It was the largest and most audacious example of a global phenomenon. A phenomenon where the official history seems designed to conceal the true methods by which the work was done. We are looking at a worldwide project, conducted over a century, which consistently presents a narrative that does not align with the physical and logistical realities of the time. The question is no longer just how they mapped India. The question is, what was the true nature of this global mapping project, and what technology was actually used to execute it? The narrative fails. The logistics fail. Let us now turn to the cold, hard logic of numbers. Numbers do not tell stories. They simply describe reality. The Great Arc of the Meridian was approximately 2,400 kilometers long. The primary survey stations, the main points of the triangulation, were set at intervals of roughly 10 to 15 kilometers. A simple calculation tells us this requires a minimum of 160 primary stations. In reality, with connecting points and baselines, the number was far greater. But let us be conservative and use 200 stations for our model. The project officially began around 1802 and its initial phase concluded around 1871. Let's focus on the most active period of the Great Arc itself, a span of roughly 40 years. If we divide 40 years by 200 stations, we get an average of 0.2 years per station. That is approximately 2.5 months per station. On the surface, this might seem plausible. But this is not 2.5 months of work at the station. This is the total time allocated for every single activity. Let's break down what must happen in those 2.5 months, or 75 days. First, the team must travel from the last station to the new one. Through jungle and desert, this could take weeks. Let's be generous and say it takes 15 days. Now they must build the observation tower. A 50-foot masonry tower cannot be built in a day. It requires quarrying or transporting stone, mixing mortar, and careful construction. Let's be extremely generous and say this takes 30 days. We have now used 45 of our 75 days. Next, the half-ton theodolite must be hoisted, assembled, and calibrated. This is not a simple task. It would take at least several days of painstaking work. Let's allocate 5 days. We are now at 50 days. Then, the team must wait for ideal weather. In India, with its monsoon season and intense heat, this is the great unknown. It was not uncommon for teams to wait for months. But our schedule only has 25 days left. Let's assume they were miraculously lucky every single time, and only needed 20 days of waiting and observation. This brings us to 70 days. Finally, they must disassemble the instrument, pack it, and prepare for the next journey. Another 5 days. We have reached our 75-day limit. This is a best-case scenario. It assumes no delays, no major equipment failures, no disease outbreaks, no conflicts with locals, and impossibly good luck with the weather, 200 times in a row. It is a mathematical fantasy. The timeline is not just tight, it is broken. There is not enough time in the day, the month, or the year to perform the work as described. And then there is the matter of precision. The survey achieved an accuracy that stunned the scientific world. The calculations to reduce the raw data had to account for the irregular shape of the Earth, the geoid, as well as factors like gravity and atmospheric refraction. We are told this was done by hand, by teams of human computers working with logarithmic tables. This was a colossal undertaking, involving millions of individual calculations. A single error, in a single column of a single ledger, could throw off the entire result. Yet, the final error rate of the Great Arc was astonishingly low. The probability of achieving this level of accuracy with a distributed, manual, human calculation system over decades is infinitesimally small. The numbers suggest two things. First, the time it took to move, set up, and use the equipment was likely far shorter than would be possible with primitive methods. Second, the method of calculation was likely more robust and less prone to error than a purely manual system. The numbers do not lie. They paint a clear picture. The official methodology and the final result are not compatible. We are faced with a series of impossibilities. An impossible instrument, an impossible journey, an impossible timeline, and an impossible level of accuracy. The official story, that of heroic men overcoming these odds through sheer willpower, is not a sufficient explanation. It is a story, not an analysis. So, what is a more logical, more controlled hypothesis? We must reject fantasy. This is not the work of ancient aliens or a lost civilization. The evidence points to a 19th-century project, using 19th-century personnel. The deception, therefore, must lie in the capabilities of that century. The fundamental contradiction is between the stated technology and the achieved result. When a result is real, but the stated method is impossible, the most logical conclusion is that the stated method is incorrect. The story has been altered. Let us propose a more plausible scenario. Hypothesis 1. The transport was not primitive. The official story of bullock carts and elephants is a cover. The survey teams had access to a form of mechanized transport and lifting that was not publicly disclosed. This could have been early, specialized steam-powered tractors or winches, capable of traversing rough terrain and hoisting heavy loads. Such technology existed in nascent form, but its application in such a remote and widespread manner would represent a significant leap. Concealing this capability would serve to enhance the myth of man over nature while hiding a strategic logistical advantage. Hypothesis 2. The instrument is a red herring. The massive, half-ton theodolites were real, but they were not the primary tools of the survey. Perhaps they were used only at a few, easily accessible, primary baseline stations to impress observers and establish a scientific precedent. The bulk of the grueling triangulation work, in the remote jungles and mountains, could have been done with a different, far more portable, and perhaps more advanced technology that was never recorded. The great theodolite becomes a piece of theater, a prop in a story, while the real work happens off stage with tools we are not meant to see. Hypothesis 3, the most radical, yet the one that resolves all the contradictions. The map data, in some form, already existed. The Great Trigonometrical Survey was not a project of pure discovery. It was a project of verification, consolidation, and retroactive justification. Imagine a scenario where a pre-existing, perhaps less complete but highly accurate, set of geodetic data was obtained. The source of this data is unknown. It could have been the result of an earlier, unrecorded survey, or acquired through other means. The 70-year Great Survey then becomes a massive theatrical performance, designed to create an official, acceptable origin story for this data. They were not discovering the shape of India, they were tracing a shape they already knew. This explains everything. It explains why they used an impossibly large instrument. It was for show, to prove the scientific basis of their work. It explains the impossible timeline. They were not searching for station points, but going to predetermined locations. It explains the impossible accuracy. They were not calculating from scratch, but confirming existing figures. It explains the missing logistical records. The true logistics were not about discovery, but about reaching specific points and staging a public-facing measurement. The Great Survey was not a scientific mission. It was an exercise in creating provenance. It was the greatest piece of historical theater ever performed. A laboratory instrument weighing half a ton. A 70-year journey through thousands of miles of the world's most hostile terrain. A map of near-perfect accuracy. The official history of the Great Trigonometrical Survey of India presents us with these three elements and asks us to accept that they fit together. But they do not. The story is broken. The physical evidence of the instrument contradicts the logistical reality of the journey. The mathematical precision of the result contradicts the stated method of calculation. The narrative of heroic perseverance is a compelling story, but it is not a viable explanation for a feat of engineering and data processing that was, by all reasonable accounts, impossible for its time. We are left with a profound and unsettling question. The map in our atlases, the very shape of a nation on paper, is real. But the story of its creation is a fabrication. What does this mean? It means that our understanding of the 19th century is incomplete. It means that there were capabilities, systems, and technologies in operation that have been written out of the public record. We are not providing an alternative answer. We are demonstrating the failure of the existing one. The goal is not to believe in a new story, but to question the foundations of the old one. History is not static. It is a collection of records, and where those records are silent, contradictory, or illogical, we have a duty to investigate. The Great Survey of India is one such case. The evidence is not buried in a secret vault. It is hiding in plain sight, in the impossible weight of an instrument, in the impassable terrain of a jungle, and in the deafening silence of the official record. Look at the old photographs. Read the heroic accounts, but read for what is not there. The questions are more important than the answers. If you believe that history is not a set of facts to be memorized, but a puzzle to be solved, join our investigation. The truth is in the details.